Hey everyone, so this video is on bond polarity, which is going to be part one of two lessons on polarity in chemistry. So you may have heard of the word polarizing or polar or poles before. We can talk about the Earth having north and south poles, or we can think about topics that are polarizing, like politics in the United States, for example, of two different sides. So how do we apply that to chemistry? We're going to be talking about sides with different charges. So specifically positive and mainly negative charges being unevenly spread out between two atoms or around an entire molecule. We're starting in this video looking at just how charge is distributed between atoms in a bond. Before we do that, we need to review the concept of electronegativity. So electronegativity is one of the periodic trends we've talked about, and it is defined as how attractive an atom is to electrons in a bond. So when we're talking about a bond, we're talking about electrons being shared, right? We also maybe can talk about electronegativity as how strong an atom is, how strongly it pulls on electrons. I know in my class I talk about protons being kind of the muscle of an atom or the muscle of the nuclei, and the more muscle it has, the better it can pull on those electrons. We also need to be able to still compare the relative electronegativity values of different elements based on where they live on the periodic table. So I'm going to go ahead and cross out the noble gases. Hopefully we remember that noble gases don't have electronegativity values because they don't bond, right? And then remind yourself that electronegativity increases going up and to the right on the periodic table, making fluorine the most electronegative of all of the atoms. So we can compare two atoms in a bond as to which one is more electronegative based on how close it is to fluorine. So let's dive into actually defining what bond polarity is. First, let's also remind ourselves that a covalent bond, just that word, co, means to share, valent referring to valence electrons, to remind ourselves of that vocabulary. So nonpolar covalent bond is a bond where both atoms pull on the electrons that are being shared equally. They have equal pull on those electrons. Whereas a polar covalent bond is the opposite, right? Atoms are pulling on the electrons unequally. And the factor that determines whether that pull is equal or unequal is when we're talking about comparing the electronegativity values of the atoms involved in the bond. Specifically, the more electronegative atom is going to have a stronger pull on those electrons. And since electrons are negatively charged, and those negatively charged electrons are spending more time with this particular atom, we can attribute a partial negative charge to that atom. We indicate a partial negative charge with a little sigma and a negative sign. It's a lowercase sigma. Oppositely, the less electronegative atom has a weaker pull on the electrons. And since it doesn't have as many electrons spending time with it, it's going to have a positive charge. And we can see that sigma and the plus sign. Let's look at some pictures to illustrate this a little bit more clearly. So up in the top left, we have a picture of a polar covalent bond, an illustration rather. This is not what it actually looks like. But you can see since chlorine is the more electronegative atom, it's going to have that partially negative charge. Those electrons are are a little bit closer to the chlorine, so chlorine's going to have a little extra negative. It's not a outright full negative charge, but it's there. Right, and then that leaves hydrogen to be a little bit more positive. You can see that chlorine is stronger, it's winning that tug of war, and hydrogen's sweating a little bit. Okay, then below that we have our hydrogen cowboys happily sharing those electrons equally because neither of them is stronger than the other, and so they're being pulled on equally. Okay, and then we can also transfer this concept to thinking about ionic bonds. In ionic bonds, we know that electrons are transferred, but in reality, it's more like being stolen or that tug of war being completely won. So the atom with the strong pull, if it's a big enough difference between who it's fighting against for those electrons, I don't think I spelled that right. Oops. If it's a big enough difference, then those electrons are going to end up being transferred to that atom with the stronger pull. We can also put some numbers on this. So if, for example, we think about, H and H, the difference in the value of their electronegativity difference is zero, right? So that's going to be a nonpolar covalent bond when the electronegativity difference is pretty much zero. If we have a small electronegativity difference, we're going to have a polar covalent bond. So one's going to be pulling a little bit stronger. And so we're going to have some slight charge differentials, but we're not going to have a full outright winner in that tug of war. And then in ionic bonds, we do have that full outright winner. Now remember, we talked about how an ionic bond is always going to be between a metal and a nonmetal. And a covalent bond is only going to be between nonmetals. Well, we talked about where elements live on the periodic table indicates their electronegativity value. Here's my loose little stair step. Okay, here are all my metals, right? They're going to be on the lower end of electronegativity, and all my nonmetals are going to be at the higher end of the electronegativity. So they're going to have closer values when it comes to their electronegativity difference. That's why they have covalent bonds. They're generally going to be more evenly matched in terms of their strength or electronegativity when it comes to pulling on those electrons. When I have a metal paired with a nonmetal, generally that nonmetal is going to be so much stronger that it's going to form that negatively charged ion. It's going to steal those electrons and become an anion, and that metal is going to lose electrons. It's going to lose the tug of war and become a positively charged cation. Okay, just to make those connections that we've already talked about a little more clear and give you a why for what's happening. What I want to do to finish up this video is look at different bonds and decide whether they are polar or nonpolar. So you're probably going to need your periodic table for this. So we're going to start with O2. Okay, I'm going to go ahead and just speed draw this. This is what that molecule is going to look like. Okay, oxygen bonded to oxygen. Well, oxygen and oxygen are the same element, therefore their electronegativity value is going to be the exact same. And so this is going to be a non-polar covalent bond. Okay, we're specifically referring to the bond at this point. If we look at CO, or carbon monoxide, okay, it's going to end up having a triple bond. It's going to look like that if you wanted to draw the Lewis structure. But this bond, I have carbon bonded to oxygen. Those are different elements. So therefore, they have different electronegativities. Okay, and so we need to figure out which one is the more electronegative to indicate something called a bond dipole. Okay, we can go ahead and decide that this is a polar bond. Okay, I have two different elements. They're not going to have equal strengths, but which one is stronger? Well, it turns out that oxygen is more electronegative, and so we can draw this bond dipole as an arrow pointing toward the more electronegative element. The bond dipole always is also going to have a little plus at the end of it to indicate the side that's partially positive and the side that is partially negative. Okay, since oxygen is further to the right on the periodic table, it is more electronegative, so those electrons are going to hang out with oxygen a little bit more than they are going to hang out with Carbon, since electrons are negatively charged, that gives oxygen partially negative, carbon partially positive. Okay, you can try HF on your own. Go ahead and pause the video, and then I'll go ahead and show you how that's going to work. Since fluorine is the more electronegative of the two, right? They're different elements. So that means this is going to be a polar bond, polar covalent bond. Okay, it's not a metal and a nonmetal, so it's still covalent. Polar covalent. Fluorine is the more electronegative, so it's going to have that partial negative. Hydrogen is going to have the partial positive. Electrons are going to spend more time with fluorine than they are with hydrogen. All right, so the next video we'll be talking about how to apply this to molecules as a whole, but hopefully you have your foundation of what makes a bond non-polar covalent, polar covalent, or ionic.